Now, sound, these are basically movements of molecules, usually air molecules, and sometimes they can travel through liquid or solid objects. Now, another requirement for sound is that it has to evoke an auditory response. So it is not enough that molecules would vibrate. It should evoke an auditory response for it to be classified as sound. Now, how does sound travel through a medium, or let's say air? So, for example, when the vocal cords vibrate or when the tuning fork vibrates, the oscillations will now produce air compressions and air rarefaction waves. So, in the diagram here, you will note that here you have your pressure waves traveling through air. So you have your rarefaction and your compression waves. Now, graphically, this is represented as the sound wave. So if you look at the sound wave from crest to crest or from throat to throat, that would be your wavelength. And from the axis to the crest or axis to the throat, that would be the amplitude. Now, when sound waves are propagated or as it travels through a specific medium, the velocity of sound depends highly on the density of the medium, and this is independent of the intensity. Meaning to say, if you look at the table, the denser the medium is, the faster the velocity, and this is independent of the intensity of the sound. Meaning to say, even if you increase or you decrease the amplitude or the intensity or the loudness of sound, the velocity would still remain the same. So looking at the sound wave more closely, so from crest to crest or from throat to throat, that would be the wavelength, and from the axis to the crest or from axis to the throat, that would be the amplitude. So the wavelength is said to be the distance traveled by sound in one period, and this is how we compute for the wavelength. So that's velocity of the sound going through a particular medium divided by its frequency. For example, if we have a 500 cycle tone traveling through air, it would have a wavelength of around 2 feet. Take note that the velocity of sound traveling through air is 1,000 feet per second. So that would be 1,000 divided by 500, we'll get 2 feet. Now let's look at a few properties of sound. So when we say absorption, this is when sound hits a soft object, so it is muffled. Deflection happens when sound hits a hard, smooth surface, so it bounces back as an echo. Refraction happens when sound is able to move around objects or obstacles. Now, this is dependent on the wavelength of the sound, such that when an object or an obstacle is smaller than its wavelength, sound is able to move around it. So this is the reason why we are able to hear sound even though we are not able to see the source of the sound. Now, in relation to light, light typically will not be able to move around objects because of its very, very small wavelength. Now, when we say diffraction, this is when sound is conveyed through a suitably concave structure. Now, this may seem that the sound intensity increases. Now, this is particularly used in the olden days when amphitheaters or public places would utilize concave structures in order to magnify the loudness or the intensity of sound. Now let's talk about frequency, pitch, intensity, and loudness. So how I've highlighted here is that frequency and intensity are objective properties of sound. They are inherent properties of the sound waves themselves. However, pitch and loudness are subjective properties of sound. They are dependent on the listener. Take note that Pitch is dependent on frequency, and loudness is dependent on intensity. So first, let's talk about pitch. So when we talk of pitch, this qualifies the sensation of sound being high or low. So this denotes the tone of the sound, and this is measured usually in hertz. So again, this is dependent on frequency. The greater the frequency, typically the higher the pitch of sound. Now, when we say pitch is dependent on the frequency, this is particularly true for sound waves around 1,000 to 3,000 cycles per second. So within that range, as frequency increases, pitch also increases, and this is independent of the amplitude or the loudness. However, when you have very, very high frequencies or very, very low frequencies, the intensity of the sound or the loudness of the sound changes the pitch. For example, if you have a tone greater than 3,000 cycles per second, if you increase the volume or the intensity, it may seem that the pitch increases. Another example, if you have a very, very low frequency sound, for example, less than 1,000 cycles per second, increasing the intensity or the volume of the sound creates an illusion of the pitch further decreasing. So in practical terms, if you will note, singers, when they belt out the high notes, they usually shout out or increase the volume of a high note. So this creates an illusion of the singer hitting the high note. So here, pitch is said to be a subjective property of sound. So this is dependent on the listener. Now, how do we interpret the tone or the pitch of a sound? So two theories were developed. First, you have the telephone theory. So the telephone theory says that pitch is determined by the cerebral cortex or the auditory cortex. So it is the job of the auditory cortex to determine the highness or lowness of a particular sound. However, this theory is no longer widely accepted. What is more prevalent is the place theory. So this states that pitch is a function of the cochlea. So it is the job of the cochlea to determine the highness or lowness of a particular sound. Now, under the place theory, you have the Helmholtz resonance theory and the Beckesy's traveling wave theory. Now, for the Helmholtz resonance theory, it is said that the basilar membrane or the basilar fibers would have varying lengths and diameters. So if you look at the fibers at the base, so length of the fiber will increase from the base as you go up to the apex or to the helicotrema. And the diameter decreases from the base going to the apex or to the helicotrema. So if you will note, basilar fibers at the base would be short and stout, and as you go to the apex of the cochlea, it gradually becomes longer and more slender. So if you will imagine the strings of a grand piano, so it is similar to that. So each string would have a specific diameter and a specific length such that they will now vibrate selectively to certain tones. Shorter fibers near the base would vibrate to higher frequencies, whereas longer fibers near the apex would vibrate to lower frequencies. Now, the Beckesy's traveling wave theory also supports the place theory. So here, the cochlea is said to be a tuned structure and the width of the basilar membrane changes. So it increases from the base going up to the apex or the helicotrema, such that it will now exhibit graded stiffness, and the mass of the organ of Corti would increase as you go up to the apex. So with that, high frequencies would cause more displacement near the base or near the stapes, and low frequency sound waves would cause displacement more near the apex or helicotrema. And it is observed that shorter wavelengths will die out more quickly, and longer wavelengths can easily traverse the entire length of the cochlea. Now, in this diagram, this is a simplified drawing of the cochlea outstretched. So the white horizontal bar would represent the basilar membrane. The green horizontal bar would represent the organ of Corti. And here we have three wavelengths. So we have shorter wavelength or a high frequency sound wave, and you have your medium, and of course you have the long or low frequency sound waves. So take note that your high frequency sound waves, they are able to stimulate the hair cells near the base, and as the frequency decreases or as the wavelength increases, so here you have your low frequency sound waves, they are able to traverse the entire length of the cochlea, and they are able to reach the hair cells or the organ of Corti near the apex.